Hi everyone, welcome to our second PES lecture. Welcome back. Today we're going to be talking about current bidirectional switches. So here we can see a realization. We have an SPST switch, but this is actually a transistor connected with an anti-parallel diode. So this allows you to have that current bidirectional function. So the combination of the two can conduct current in either direction. So when IFT is positive, we can conduct through the transistor, I can't speak. And when IFT is negative, we can conduct through the diode, which is the opposite direction. So we can use a bipolar transistor here like a BJT, or we can have a MOSFET or an IGBT or any other single quadrant switch. So although this device can conduct current in either direction, it can only block voltage in one. So if it blocks an off-state voltage that is positive, both devices can be off. But if we reverse the direction of the voltage, you can see that the diode would turn on and then short out the voltage source. So in conclusion, this device can only block one polarity of voltage. So you can see that here in the IB characteristic that I drew, you can see that you can conduct in either this quadrant, or in the next section, I'll talk about how you can switch it over to operating in quadrants 2 and 3. So here I'm going to formally introduce the two-quadrant switch. The two-quadrant switch is a combination of a transistor and diode, and then have this composite IV characteristic that I just showed you in the previous section. And we can see to the right, we can see the axes of the off-state voltage and the on-state current. And then we can deduce from that that we can operate in either quadrant 1 or quadrant 4. Okay, so if we want to build a current bidirectional switch that operates in the second and third quadrants, then all we have to do is connect our transistor and diode backwards, meaning that we can just define the polarities in the opposite direction here, and then we can get that result. So let's talk about MOSFET body diodes. The MOSFET, as we mentioned before, is in fact a current bidirectional switch itself, so the MOSFET channel can conduct current in either direction. Additionally, it has this body diode that can conduct negative current right here. It may not be a very good one, and we may not want it to conduct at all because it has a slow switching time. But if you really have to, you can put an external diode in series right here with the MOSFET that only lets current flow in the positive direction. And then you can put an additional external diode in parallel to get the current flow in the opposite direction right here. At low voltages, you may want to offer a MOSFET with a good body diode, or at high voltages, you may want to use an entirely different device like an IGBT, which is already co-packaged with anti-parallel diodes already built in. So let's look at a simple inverter. Here we have a two-quadrant switch application where we have a split DC input voltage. We have plus VG into the converter, and we have minus VG at the bottom. We have a load, right over here, that we want AC voltage over. And each of these, Q1 and Q2, are current bidirectional switches. And if we succeed in producing an AC output, the current in our load is also AC and can go in either direction. So let's get rid of these circles for now. Okay, so this will also coincide with our inductor current, which can go in either direction as well. So our switches can conduct either polarity of current. On the other hand, the switches block DC input voltages. So let's say this switch is on and the bottom one is off. The node between them now is pulled to plus VG, and the voltage across the lower switch is now plus VG minus a negative VG, or 2 VG in DC. And now our DC input voltage does not change polarity. So this bottom switch will now have to block a positive voltage. So the current bidirectional switch application will work here. And actually, many applications of the current bidirectional switch are in inverters. But how really does this converter work? This is like looking kind of crazy right now. So let's clear up some space. Let's sketch the voltage at the switching node, right? So let's draw a little graph right here. Oh God. So let's see. Let's do if the first switch is on, the node is at plus VG for some duty cycle, and plus VG for some duty cycle of T of S. And then when the second switch is on, we're at a negative VG for a D prime duty cycle of T of S, where D prime is equal to 1 minus our original D. Then our cycle is going to repeat forever. The average value of this waveform is going to be D times our initial voltage at our first interval, and that is going to be our VG, plus our D prime times the voltage at the second interval. And then let's just rewrite that as D times what we said the voltage at the first interval was VG plus D prime times minus VG. And rearranging this, we can do VG times D minus D prime. And then what do we define D prime as? This is 1 minus our original D. And we're going to get VG times 2D minus 1. So the low frequency component of this waveform gets filtered out by the LC on the right side, and that is what is applied across the output load. So let's draw a plot of that function that we just solved for, our V naught of t. We have max being Vg, and we have our minimum being negative Vg. This will probably not be to scale, but whatever. We have D here, and our max duty cycle is going to be 1, and then our midpoint is 0.5. So let's draw it like this. So if our duty cycle is 0.5, our function is obviously going to 0. If our D increases, you get a positive voltage, and vice versa. So as we vary the duty cycle about this like half mark, our output voltage will also vary sinusoidally about our 0. If you plug the D of t function into the V naught function that we solved for, then you can find that the output voltage is sinusoidal as well. So let's say you want a 60 hertz output. Then you can make the modulation cycle also be the same as what you want at your output. So you'll also make it 60 hertz. The inductor current, which is also the load current, also acts sinusoidally. And this can either be positive or negative. So we absolutely need to have current bidirectional switches here. So here is a 3-phase version of the exact same circuit. So we have a 3-phase AC Y load here, and we can vary each of the 3 phases duty cycles sinusoidally, offset by 240 degrees, and then we can drive a 3-phase load like a motor, or even build an inverter to connect to the utility. So again, the switches have to block DC input voltage and then conduct the AC output current. So this is fundamentally a current bidirectional application. Okay, this is one of my favorite examples. This is a bidirectional battery charger and discharger. This is a DC-DC application, which is like basically a buck converter where our DC input voltage is VG of some bus voltage right here. And one example is a space main power bus. The load here is replaced by a battery that can either store or supply energy as opposed to a passive load like a resistor. So when the battery is charging, we have power moving this way to the right. And the circuit acts like a buck converter if you look at Q1 and D2. If we want to supply energy out of the battery and back to the bus, we reverse the direction of current, and in that case, Q2 and D1 are conducting. And it's whenever Q2 is off, we can turn Q1 on, and vice versa. Operated together, we have this great combination of current and bidirectional switches that conduct current in either direction, depending on whether or not we're charging the battery. And the reason why I'm using a space power bus as our example and why I'm so excited about this example is because this DC-DC application is really popular in space. They have DC power supplied by solar panels, and when the spacecraft is eclipsed, like by some external planet like Earth, then batteries need to be used as backup. I really hope you enjoyed learning about current bidirectional switches. Um, in conclusion, we can build these current bidirectional switches by basically as a parallel combination of a transistor and diode, and you have all these different kinds of really cool applications. So hope you learned something and see you in the next lecture. Thanks.